So we said fine soils are relatively less permeable than coarse soils. Flow is more difficult. Water takes longer time to drain out of the pores. Now, just consider this little statement from the point of as a concept, because we haven't talked about flow and permeability and that kind of things yet. But this is an intuitive knowledge you can figure out. So how does that affect stress calculations? Let's make an analogy here. Our analogy is going to be this. So I have this piston. So here is my piston. And basically, I'm going to be pressing on this piston with total stress. So yes, this piston is going to represent my soil. Inside my soil, inside my piston, I have compressed spring. So this is going to represent my grains, and there is water inside the piston that represents the water inside the pores. And this piston is tight, has no leaks, etc. Now I'm going to put another this time it's the same thing, but with one exception. The exception is that my piston has a hole. So again, it is the same piston, everything is the same. So this is also the same effective stress, same total stress. I know I'm drawing them like forces, but assume the piston's area is 1. So this is just an analogy. I'm not going to do calculations with it. And let's say that U comes from up here. The pressure can equilibrate because I have a hole in here. Now, both of them are in equilibrium, and Terzaghi's effective stress principle work for both of them. The total stress is carried by effective stress plus pore pressure in both of them. The question is, what happens if I add some additional stress, additional total stress? Now let's consider the first piston. Here I have a sealed piston, sealed rigid piston with water which is incompressible for the purpose of this example. So I have an incompressible fluid in a sealed piston. No matter how much I press on it, it's not going to get smaller. So one thing I know here is there will be no volume change. If there will be no volume change, I cannot compress the spring. So if I cannot compress the spring, I cannot make the stress in the spring increase. So if I cannot compress the grains, therefore the effective stress, somebody has to take the extra stress. So that somebody is going to be pore water. Whereas in this one, because I have a hole, water can come out. And as the water comes out, I will be able to compress the spring. And because through the hole, my water pressure inside the piston is still in equilibrium with this water surface up here, the water pressure is not going to change. So the effective stress is going to take the extra load. So here oh sorry, delta U. And in this one, there is delta V, delta V, there is volume change. And changes in total stress induce changes in effective stress. So I'm going to give names to these. This is the undrained, and this is the drained behavior. Now, which one is which? Obviously, this first piston, the undrained piston, doesn't let water escape, so it should be representing fine soils. Now, given enough time, water will flow because it is not completely impermeable. Even the fine-grained soils allow the water to move a little bit. So, given enough time, the water will be able to flow. So that means the coarse soil is drained always. Fine soil is undrained immediately after stress change, and drained after a long time passes. So this is important, and I should also add here short time, long time distinction. Depends on the rate of load as well, and soil permeability. So for example, if I load a sand very rapidly, then for the first few seconds the water will not have enough time to escape. So it might act as undrained for a few seconds maybe. So that is in very fast loads like earthquake, for example. But anyway, most of the time undrained is fine soil, short-term behavior. Drained is everything else. So there is one more little detail that we have drawn in our analogy though. My piston is filled with water. What if it was filled with water half of the way and the other half was air? Then no matter how well sealed your piston is, the air would compress. And for this to work, you have to be preventing the volume change, or the soil has to be unable to change its volume. So it has to be saturated. Otherwise, if you have air, then you can always compact the soil. So let's consider one more example here. So I'm going to do the usual. So here I'm going to have sand 0, 3, 5, and let's say 8. I have clay here. And of course, let's put some unit weights in. Let's say its gamma is 16. This one's gamma saturated is 19, and gamma saturated for the clay is, let's say, 18. And in this problem, I'm going to be adding a wide area load of 25 kPa, or let's make it 32, just make calculations easier, 30 kPa. So and of course this blue line I drew is the water surface. So the question is, or the questions are, first, part A, for load. Part B, immediately after load. And part C, a long time later. So before loading, I'm going to have 48 here, and for simplicity's sake, let's not have capillarity here. But if we had capillarity, it wouldn't be any different from what we did earlier. Then I have 2 meters of 19, so that is 38 plus 48 is 86. And then I have 3 meters of 18, that's another 54, so that gives me 140. Next is the pour pressure. Pour pressure, I have 0 here, I have 20 here, 50 here. And by the way, let's have some more sand below the clay layer, so that we have one more thing to show down here. So obviously, as we go deeper, these continue. Actually, I messed up my color coding. Sorry about that. Let's make this brown again. And then my vertical effective stresses are going to go like this. It goes to 48 here. Then 86 minus 20 is 66. Then 140 minus 50 is 90. Now, let's move on to part B then. I applied 30 kilopascals of additional load. What happens then? Actually, let's make this 50 so that I can draw more clearly. So I'm going to apply 50 kilopascals of load. 50 is somewhere here. So I'm going to be adding 50 everywhere. So I have 50 here, 98 here, 136 here, 190 kilopascals down here. The load just is applied everywhere because this surface load is very large. So it goes on to a long distance. Now for sand, sand is going to be drained in the short term. Therefore, for sand, the pour pressure isn't going to change. Whereas for clay, for immediately after loading case, clay is going to be undrained. That means my effective stress is going to be constant. So I can figure out the rest from this. So this goes up by 50. The water pressure didn't change here, so all the stress increase is taken by my effective stresses. So I have 50 here, 98 here, and 116 here. And then I have a discontinuity here because in the clay, my effective stress cannot change. And if I have another layer of sand below, it will continue again from 140. But here it is still 66 to 90. But that means I have to make that same discontinuity on the other side for the water pressures. So here it is 70, here it is 100. So here is your change in stress taken by the water. And here in the sand, in the drain behavior, your change in stress is taken by the effective stress. And of course, it is able to continue from here if you have a sand layer at the bottom as well. Then what? Then a long time later, weight of my soil layers and load didn't change over time. So a long time later, my total stresses are the same. A long time later, this also became drained. So everywhere I'm going to have the same initial pore water pressures of 20, 50 and so on. And that means everywhere I have this increased stress. So basically this is it, but there are other things we can do with this as well. So for example, I could be excavating the soil. Or so if I excavate the soil, I'm basically removing load. So I still would have delta sigma, but it would be a negative delta sigma. And I could also change the groundwater level in my soil. No matter what I do, the undrained soil will have its effective stress constant. So changing the water level or excavating some soil, reducing the loads, just think, instead of saying immediately after loading, I could have said immediately after excavation, immediately after water level is changed. So in all cases, you have to separate for any given time, either immediately or a long time. You have to think, are any of my soils doing undrained behavior? If they are doing drained behavior, it is simple because it is straightforward. Total stress is weight of everything above that. Pore pressure is hydrostatic. So effective stress is their difference. That's it. Drained is very easy. For the undrained behavior, to make it easy, you have to remember drained, undrained, it doesn't matter. Total stress is always weight of everything above. And in undrained mode, effective stress remains the same. effective stress doesn't change. So if you remember this, undrained means effective stress doesn't change. Then you can figure out the pore pressure back from there.